and reduction and stuff, as well as the I don't know what they're called, sections.
Grignard?
Are you gonna be posting? Yeah, are you gonna be posting the actual SI sessions or just those videos on your YouTube account?
So I've been posting both. I don't know if Wednesdays is visible, but it should be up on there. So I will be posting both.
Okay, thank you.
You're welcome. I just figured the sessions are a little bit weird sometimes. Like the audio doesn't always work. Sometimes it lags and like it gets choppy and I forget to record. So I thought it'd be nice if you guys had like just the actual content in a video, like yeah, in that format.
Yeah, I really like those. Those are good.
Good, yay! I actually, fun fact, forced Chris to help me record some stuff yesterday, so he will be popping up in some of those videos. So I'm excited for you guys to see that. But for now, any more questions before we go back to this? Someone said we love Chris. He loves you too. No? Okay, sweet. So now we're going to talk about the stability of dynes because surprisingly, or maybe not, conjugation brings a really high level of stability. So the more conjugated you are, the more stable you will be. And between conjugated, isolated, and cumulated, we can also show a difference of stability there. And what I mean by that is we already said conjugation makes it super stable. So we know that this is the most stable type of dyene that we have. But we also have to compare isolated and cumulated. So between isolated and cumulated, which one do you guys think will be more stable? You can either put I or C in the chat. Ooh, I got a 50-50 split. Okay, so someone who said isolated, you want to volunteer as tribute and do like a quick explanation of why you think so?
Never mind.
No! You can literally say anything. I'll never judge you. I promise.
Does that do with like, SP2 and all that, or no?
It's actually even simpler than that, but I'm glad you're thinking about transition. That's awesome.
Yeah, that was all I got.
Okay, that's fair. Someone said more resonance. Not exactly. And the reason I say that is because it cannot resonate through this carbon. So conjugation has a whole lot of resonance, but isolated does not.
What about steric hindrance? That's my last one.
Okay, cool. So why do you think steric hindrance would make this better than this?
Because that one, the cumulated is like both the double bonds are like closely near the carbon versus the isolated is kind of spread out.
Yes, exactly. So it's because isolated has more space between everything. Everything's not like densely packed and in each other's space. So cumulated, on the other hand, is all shoved together in one little area, so it's not as stable. So cumulated is the least stable. Isolated is like meh, it's in the middle, it's whatever. Conjugated is super, super, super stable. And then between conjugated molecules specifically, the more conjugation we have means that we will have more stability. I have no idea what's going on outside. Ta-da! And so what I mean by that is how many double bonds we have in conjugation. So something you're going to hear me say is level of conjugation. Usually level of conjugation. And what I mean by that is, I feel like I got the same exact 20 times. That's cool. Okay, is it okay if I do a session? Okay, cool. Sounds good. Okay, sorry guys, I got distracted. So basically when we say level of conjugation, we just want to quantify how many double bonds are in conjugation on the molecule. So the smallest number we can have is 2. Well, let's say we have 3 or 4, right? Which one of these will have the highest level of conjugation? 1, 2, or 3? 3, cool. So of these, which one will be the most stable? Awesome, cool. So the higher the conjugation, or the more the conjugation, the more stable. So in my opinion, this is pretty straightforward. Not too much like in-depth chemistry stuff you actually have to know. So yeah, do you guys have any questions about it so far? And I'm also going to take my mask off. I don't know if you guys can even hear me properly. I haven't gotten anything in the chat yet, so I'm going to assume that's a no. So we're going to move on. And we're actually going to go to the actual handout and do some examples. So usually I'll put you in groups, but I just genuinely don't feel like it. So sorry. But in the first answer choice, or in the first row of molecules between 1, 2, and 3, which one is conjugated? Tell me in the chat, pretty please. Okay, 3 people have said it so far. Let's have a couple more. Okay, cool. Most people are saying 1 would be conjugated.
3, it wouldn't, excuse me, wouldn't the last one be conjugated too?
No. And the reason it wouldn't be is because we have a carbon in between the 2 double bonds. So there's 2 single bonds.
Sorry, I meant the compound beneath it.
Oh, yeah. All those are just a different set of questions. But this one, yes, would be conjugated. You're right. So I guess I can just write that. Okay, so just sticking to the top row, can you guys tell me which one is isolated? 3, cool. And then which one is cumulated? 2, okay, cool. That one was an easy one. So in the next row, super quick, 1, 2, 3, which one is cumulated? Yes. As you can tell, I wasn't very creative with these questions, and this is isolated, but it will really be that straightforward. He'll usually just in condensed formula give you a couple questions or a couple choices, and then you have to pick like which one is cumulated, and it tends to be super straightforward because okay, let me show you one instead of just talking. It'll be something like this. So which of the following dienes would be cumulated? And then he gives you all these choices, and you have to just find the ones that have 2 double bonds on the same carbon. But now, just for practice, I'm gonna point to one, and you guys have to tell me C for cumulated, CO for conjugated, or I for isolated. So answer choice A, what do we think? Isolated, cool. Answer choice B. Most people are saying conjugated. That's absolutely right. And the reason we know is because it's double, single, double. We already know that C is cumulated. What about D? Conjugated, sweet. And then what about E? Isolated, perfect. You guys are killing it. You guys are already professionals.
Excuse me, what did you say about D again? And you said it was conjugated? Or no, it's not.
I'm sorry, what? Which one are you talking about?
I'm talking about D on the multiple choice. Was that not conjugated or was it conjugated?
It is conjugated, so I'll write it here. Isolated, conjugated, accumulated, conjugated, isolated. I hope that makes it a little bit more clear. Any other questions, or can I switch back to the handout? And don't be afraid to ask questions just because I say it like that. I love questions. No? Okay, we go back. So someone pointed out to me last semester that yes, technically this molecule won't exist just like this because it has a lot of steric hindrance, but I was trying to be cute because it was Valentine's Day. So it's a heart for Valentine's Day. Doesn't matter. For this question, we're only looking at number of double bonds in conjugation, right? So that's all I want you guys to pay attention to. One thing I will point out, though, before I ask you guys to help me answer this, is there is an aromatic effect when it comes to conjugation. So we're going to talk about this in chapter 14 because you guys haven't learned about aromaticity yet, but I'm just going to write aromatic is more stable than conjugation. And so what is the one aromatic compound you guys have been working with since day one of Orgo? Benzene! Yay, our best friend benzene. And then someone asked about the order of like primary, secondary, tertiary, allylic, benzylic. It's not at all like that. So here we're actually just talking about the molecule itself. So if I had this sucker, actually, even better example. I'm going to go back to this blank page. Bam. Whatever, that's literally good enough. Okay, so let's say I have 3 cyclohexanes, right? And then this one is just going to be all by itself, just an alkane. And then let's say we have a diene here. If we have the diene and then we compare that to the benzene, yes, this conjugated diene is way more stable than this. However, or even just for a solid comparison, like this, right? They're both dienes, but one of them has isolated, one of them has conjugated, but then this is conjugated. Oh, I'm so sorry. This is conjugated, but it's also aromatic. And so aromatic is like wildly stable, super amazingly stable, the best stability you're going to get in Orgo. And someone said, what makes something aromatic? I don't want to go into detail right now, but essentially it has to be cyclic, planar, and fully conjugated. You won't have to know those rules for this exam. You will for sure have to know them for the next exam, but this is enough for now, just so you guys know.
Excuse me, it is so stable, that's why we draw a circle on benzene, right?
Kind of. It's not necessarily because it's stable. It's more so because the electrons are dissociated, or not dissociated. They're basically dispersed around the entire ring. So every single carbon has an equal chance of having the electrons at any given time. So that's why we draw a circle.
Sorry, so you mean like it can delocalize like completely?
Yes.
Like if you were to do resonance?
Yeah, so it has complete delocalization. That's what makes benzene so special. If you guys want something really interesting to look up high stacking. That's really fun. But I'm not going to talk about it because it's not a big deal. Okay, so how many double bonds do we have in conjugation for molecule number 1? I want you guys to tell me in the chat. 4, perfect. Okay, what about molecule number 2? 2, sweet. And number 3? 4. But we have a what here? A what kind of ring? Benzene, yes, and benzene we know is aromatic. And then this last molecule has how many? 5, sweet. Okay, and you guys don't know this yet, but this is also aromatic. Not a big deal. I'm just telling you because people have been curious in the past. So I will write here aromatic. Like I said, you don't need that to answer the question though. So between these, which one is obviously the least stable? 2. And the reason why I say obviously is because these have 4, 4, and 5. This one only has 2 double bonds. It's going to be the least stable. And then next up, we have either 1 or 3. So between answer choices 1 and 3, which one of those will be more stable? 3, cool. And I'm pretty sure I repeated myself too many times. But the reason for this was because benzene is super, super stable because it is aromatic. So even though they have the same number of double bonds in conjugation, answer choice 3 has the extra stability from being aromatic. So if we're putting it in order, it would be 2, and then 1, and then 3. And then number 4 is the most stable because it has 5 double bonds in conjugation, plus it has an aromatic compound. So I guess I didn't need to write anything. Sorry. But yeah, so the order from most to least stable is number 4, number 3, number 1, number 2. Any questions? No? No questions? Good. Okay. Hopefully that means I'm doing something right. So I'll leave this for like 10 seconds while I get a sip of my coffee. And then you guys can screenshot and whatever you'd like. And I'm just going to read the chat really quick. Okay, so someone asked about longer versus shorter bonds, and we're going to talk about that, just not necessarily right now. So put a pin in your question. Not that it's not important or anything. I just don't feel like getting really off topic. And then someone said, is there added stability because it's a ring? I'm hesitant to say yes because it depends on the size of the ring. So generally speaking, the more members you have in a ring, the more stable it gets. But it's not necessarily ring equals more stable. Because if you had a linear compound versus like cyclopropane sucks. It's not stable at all. And then someone said something about a biphenyl group. I wasn't really sure what you meant by that. So if you want to unmute and ask, that's fine. But if not, we're going to go on. And then someone asked if we're going to do UV spec. I don't know. Depends on how far we get. Okay, cool. So let's go on. So the next thing we're going to talk about is configuration versus conformation. And this is really important because, one, he'll just straight up ask you some questions about configuration or conformation. But furthermore, we're dealing a lot with double bonds now, and it's important that we're naming things correctly and we understand how stability works. Sorry, I feel like I'm going to sneeze. Anywho. So I'm going to draw a line right here. This is configuration. And this is something we've seen in Orgo 1. And then this side right here is conformation. And it's kind of a mouthful when you're trying to say all this, so if I stutter a little bit, please excuse me. But as far as configuration goes, we are looking at one double bond in between two single bonds. So how I want you to think about it is a single bond sandwich that has a middle layer of a double bond. So one more time. It's a single bond sandwich with a double bond in the middle. And the way we name this is with cis, trans, or EZ naming. Cis, trans is not the best way of naming, so we're going to stick with EZ. And so when we're naming, just as a review, we cut the double bond in half, right? And then we're looking at the left side and the right side. We're picking a priority group, and then we are going to then explain the relationship, I guess, of the priority groups. So between a carbon and a hydrogen, the carbon is a priority. Same thing on the other side. And so since they are pointing opposite directions, would that be E, which is synonymous mostly with trans, or would they be Z, which is cis? Most people in the chat already said it. Cool. So this is E. And so the other one, when they're pointing on the same side, would be what? Z. Cool. The way I remember this is I had a French professor, and he always said it is on the same side. So if you think about it that way, Z is on the same side. Again, we could have also called this trans and this cis, but again, this is the preferred, more correct way of naming. And so all you really have to know is that E is more stable because of less steric hindrance. The further these two groups are from one another, the more space they have. Also, you cannot have rotation on a double bond. So you cannot flip between E and Z.
Excuse me, would C have a higher boiling point?
What was that?
I mean, like C, due to like how it's drawn, would it have a higher boiling point?
Oh, a boiling point. To be honest, if we were just looking between these two, I think so, but I don't know. When we have a longer chain, I know the more trans you have, the lower the boiling point. But in a 4-carbon molecule, I don't know if it would be that big of a difference. Sorry if that's not a great answer, but I'm not actually sure. Okay, so that's all you really need to know for configuration. Moving on to conformation. Now we have a double bond sandwich with a single bond in the middle. And this time we're going to focus on cutting the single bond in half. And now we're not picking priorities or anything because we are only looking at the double bonds. So, bam, 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 bam. And And the way we name conformations is S-cis or S-trans. So if they're pointing away from each other like this, it's considered S-trans. And so if they are pointing the same direction, it is S-cis. And if you guys had to guess, which one do you think is more stable? Trans, exactly. And again, that's because of steric reasons. So the further the double bonds are, there it is. Excuse me. So the further the two groups are from one another, the more space they have, the happier they are, the more stable they are. The difference here is that you actually can go from cis to trans because you have rotation. So you can flip between S-cis and S-trans. And someone asked, what does the S stand for? I don't know. It doesn't really matter. I mean, maybe it matters to you, but I don't know. Any questions about this before we do some examples? Okay, cool. Doesn't look like it. So we are going to identify these as either S-cis or S-trans, and then we're going to decide which one is more stable. So if we're looking for S-cis or S-trans, are we looking for configuration or conformation?
Conformation.
Yes, exactly. So we are going to split the single bonds in the middle, and I'll highlight the double bonds. And so this one that I'm circling right now, is that S-cis or S-trans? Cis, and this would be trans, super. So which one would be more stable? S-trans, cool. All right, so we have that, but I also want to take this as an opportunity to practice configuration. So I'm going to split the double bond. And now one group is down, the other is also down. Is that E or Z? Z, super. And now the other side, up, down, or left, right. You can think of it whatever way you want. E, perfect. So on the other side, let's split them in half. Down, down. So this is Z. And then we have again up, down. So this is what? E, cool. I don't know who keeps coming in now, but that's fine. So both of them have one Z and one E configuration. So that means configuration is not really the one that's in play here. We have to look at conformation, and as you guys said, S-trans is more stable. So this molecule is the more stable one. Any questions? Someone asked, can we rotate S-trans to S-cis through resonance? You can do resonance, but you don't need to do resonance in order to rotate it. Since we have a single bond here, you would just rotate the single bond to go from cis to trans. But good question. Alrighty, now the last kind of off-topic topic I want to cover is stability of double bonds. So this is kind of, oh, before I do that, I'm actually going to send you guys this because I forgot to do it earlier. Please sign in at some point. I appreciate you if you do. And I'm going to take that back off. So this isn't in the handout because it's kind of a review from Orgo 1, but kind of also not really because I don't know if they talk about this every semester. Stability of double bonds. So I'm going to go ahead and draw out a few double bonds so we can practice. So when I say something is a substituent of a double bond or substituted double bond, we're not considering hydrogens. So hydrogens do not count as substituted, they just exist anyway. So if we only have one carbon and 3 hydrogens, this is a mono substituted. If we have 2, and we can actually have 2 different ways of having di-substituted. And it doesn't matter if they're E or Z in this case. I just want to show you 2 substituents on the same carbon, but 2 substituents on opposite carbons. That's important, but I'll go back to that in a second. If there are 3 substituents, we call it tri-substituted. And if there are 4, we call it fully substituted, or I think it's quadra-substituted. But Dr. West only really says fully substituted. The reason I am bringing this up and the reason why I brought up these 2 is because it makes these questions a lot faster if you can just look at 2 double bonds and without anything else know which one has to be more stable. So if you have something that's mono-substituted compared to tri-substituted, it doesn't matter what the groups are. It doesn't really matter what the configuration or conformation and whatnot is. Tri-substituted is always going to be more stable than mono-substituted. So the order of stability goes from left to right, left being least stable, right being most stable. And this is something Dr. West, I don't know if he covers it in his videos, but he definitely has it in his PowerPoints. So between the 2 options for di-substituted, having 2 substituents on opposite carbons is more stable than having 2 substituents on the same carbon. And I'll zoom out so you guys can kind of see everything. And someone asked, is that because of sterics? Yes, there's probably other effects going on too, but sterics is a big one. That was a good question though. Any other questions as far as this stuff goes?
Does this have to do with geminal or vicinal, like for the di substituted, or no?
Yes, we can also think of it that way. So these would be geminal to one another. Oh, I won't write the whole thing. And these would be vicinal to one another. And so vicinal, just one more time, means on adjacent carbons, and geminal just means on the same carbon.
So vicinal would be more stable?
Yes, in this case. But
Thank you.
you're very welcome. But 9 times out of 10, if he's going to ask you about stability, he's not going to waste his time comparing these two because they're almost the same. He'll do like mono versus tri, or di-substituted versus fully substituted. You know, that kind of thing. But you guys are asking great questions. Someone unmuted for a second, and I was like, my ears went up. So this question I actually am going to leave for the opener of next session. And the reason I'm doing that is because I want you to try it out. I want you to go through and find the configuration for each of these double bonds. And then I want you to find the conformation for each of these molecules. Okay? It might take a while, especially if you're doing it like for the first time. It may take a couple minutes, but once you're able to do it once, you can breeze through it again and again. So you'll be really prepared for the exams. So with that being said, I wanted to use the last couple minutes to do a really quick summary, and then I'll give you guys a peek at UV spec. So essentially what we covered today is, what is a diene? Well, we know that a diene is 2 double bonds, diene. We covered conjugated, isolated versus cumulated systems. Conjugated being 2 double bonds that are 1 single bond apart. Isolated means they're far apart, and cumulated means they're on the same carbon. And then we also learned about the level of stability for these. So we know that conjugated is super, super stable. The only thing more stable than conjugated is aromatic. And we know that cumulated is crappy. Then we also did some fun examples. And so we know that the more double bonds we have in conjugation, the more stable we'll be. And along with that, we also know that the number of double bonds in conjugation is also called the level of conjugation. And last but not least, we covered the stability of double bonds and also configuration versus conformation. Any questions about any of that? It's kind of a lot, but also they're all interconnected, so I feel like it wasn't too much.
I have a question.
Yes.
Okay, so we went over the stability of diene. How do we know whether to look at the level of conjugation or if we should look over like the substituents like we just did with the carbons?
Great question. So if he asks you to compare a molecule that has like a fully substituted double bond, but there's only one of them, versus one that has 3 double bonds in conjugation, it doesn't matter if those double bonds are necessarily primary or mono substituted or fully substituted, they're still conjugated. So the conjugated system overall will be more stable in that case. However, that being said, if he gave you like one of these dienes, right? And let's just focus on this one, because this is conjugated, right? But if he asks you to compare the stability of this double bond to this one, then the substituents matter. So this actually isn't a great example, but let's say I gave you Actually, there we go. Right? So molecule number 1 has a monosubstituted and a disubstituted double bond. And number 2 has a fully substituted double bond. So that would mean this one is still less stable overall than this molecule. And that is because, again, it has the stability from conjugation. However, if he only asked you like between this double bond and this double bond, we know that this one is mono-substituted, this one is di-substituted. So that one would be more stable. It's kind of weird, but did that sort of kind of make sense?
Yes, it did. Thank you.
Okay. You're welcome. And then we are pretty much out of time. So to end, I'll give you a sneak peek at next week. UV spec is essentially just spectroscopy that tells us about the level of conjugation. And we do that through UV vis light absorption. It's not too complicated. So yeah. I hope you have a great day. And then I'm going to send this once more because I have to. Have a good one.
Could you go back to the page really quick, just the confirmations? I just forgot to write something down.
Yeah, no worries. Here or on the other page?
The other page.
Yes, indeed.
Thank you.
You're very welcome. And then someone asked if they can talk to me if everyone else leaves. Of course you can. I will stay for you. And then someone said, I think you said this, but is fully substituted more stable than mono-substituted? Yes. In general, fully substituted would be better than mono-substituted. The only reason in that one example it wasn't is because it was comparing a conjugated system to only one double bond. You are very welcome. Okay, so if nobody needs the handout anymore or for me to go back to anything, I will stop sharing, but I will stay on a couple minutes because someone wanted to talk to me. So let me know if you still need this. Sounds like a dog barking outside. This building is so weird. End meeting. Oh, no.